Everybody doing good? So excited for robots? Great. All right, so any questions before we get started? Good. All right, I'll probably grade your first paper summaries tonight. Spent a lot of time trying to dig through what are world models for next lecture, and I don't know, the literature there is a kind of chaotic mess of stuff intertwined together. We'll see what we can make of it later. Awesome. Besides that, I'll probably also post some stuff related to the project. So like more than half of this class is basically a project related to the topic. And by that, I just mean like in a couple of weeks, you'll put together like a one-page thing that says like, this is what you want to do. I do this pretty early also just to see whether or not I need to find any hardware for your projects as part of the larger reason I do it early. So let me know if you have any questions about that when we get there. Great. All right, so I wanted to include one more paper on doing behavior cloning, so it wasn't just all of robot arms and nothing else. But basically this recipe can work, still pretty well for even being able to use transformers and be able to collect all the data together. And it's really a very similar recipe, although in this case, well, there was a fair bit of data that was collected from people. And then in this new case, for being able to train a bunch of, or at least in this case, 1 or 2 humanoid robots. These are insanely expensive and very breakable. So you only get about 1 or 2 of them if you're an academic lab. But basically you can collect a bunch of data one way or another And what's nice about this too is that, for a lot of these robotics problems, there's already some amount of data available, like whether or not there's a bunch of model-based controllers that the community has been working on for years. That'll give us a bunch of data, possibly get some motion capture data, but this normally doesn't include the actions from the actual agent that could be used. And occasionally, you can try and get some data directly from internet videos. And then the combination of these, in this paper, you can train basically a transformer that just takes in states and actions from a bunch of these different possible avenues to get data from. And then from this, you can take this nice little robot, be able to run it in a bunch of different terrains, at least around the San Francisco area. It's done by a couple of colleagues at Berkeley. And I mean, it's nice because this is it's solving a nice bit of a control problem, and it ends up still being pretty robust. Because we've talked a little bit about, like already, when you do behavior cloning, sometimes your error should propagate depending on how long you're trying to predict and plan into the future. But in this case, when we're doing, the process of being able to train a humanoid to walk, that basically whole process is kind of like correcting error feedback, because we know that there's already a motion controller for being able to get this thing to walk. And in all these cases on the right, it's just like the slope is going up or there's rocks under the feet. So it's just a really fast and good feedback control system. And you can control this for doing like a couple of different velocities and things like that. So this doesn't use vision actively. It's kind of got its eyes closed and it's trying to walk without falling over. And you can train this pretty quickly just using a combination of buckets of data from other kind of pre-created humanoid motion. And this is also partly why there's a lot of interest in this area, partly for this bottom reason. There are tons and tons of videos of things that look slightly similar to this. The knees go the other direction for the rest of us. But then there's a lot of this data available to potentially train this like morphology for the robot, which makes basically the distance between the gap between the data you collect and like that you collect from a person and how it actually goes on the robot very small. And that can be really important as well. We'll talk about that a little bit more on Friday, but like types of data you collect have different amounts of like, how hard is it to transform this data onto the robot in some ways, if it comes from a person, or if you're trying to like copy data and move it from something that looks like an ant or a spider onto like a cow, etc.
So this model does the real-time error correction to follow the correct trajectory in a sense.
Basically, and that's a lot of what it's trying to do.
And at what frequency does the error correction?
I don't exactly know that question, but I'm going to guess this is going to be 30 to 60 hertz, because this is still using a transformer, so it can't be super fast. It's still reading in some amount of states from T, whatever, and beyond. So the fastest I've seen in this area are things around 30 hertz, which is pretty fast because all the stuff for these projects are about 3 hertz. So you can't do anything fast. You don't really get enough time to react. And we'll talk a little bit more about these later because a lot of work goes into making kind of like the low-level controller that takes in some of the commands. I guess these are mostly behavior cloning for this one, but for some other papers we'll talk about, if you're familiar with like the Seikan paper, that one they like basically put a lot of effort into making a robot controller that can take like a text goal and then it can operate for like half a second and not run into too many issues. But a lot of it is because of the work they put in the lower level controller, which is more like this. Like how do you control that frequency? And this, I believe, still takes in like a velocity command that says like what direction it should walk and how fast. So there's kind of a lot here. A lot of these control problems are kind of split into these two. Especially now since more language models have come along where they're good at kind of giving the waypoints for like where to go. They're not so fast and accurate at doing this like quick feedback control for now being robust. And you can come along and I don't know if you've seen some of the videos where people like kick their robot and it still maintains balance really well. So it's all that robust control. That's not really the long-term navigation planning yet. Great. Other questions? All right. So then we can go back to this topic. So It's great that we can do behavior cloning. When can behavior cloning fail? Partly because of, some of the complexities, and when we dig into things a bit more, we can start to see the issues. So this is one example that I showed briefly at the end of lecture last Friday, where if we have, let's say, someone or some other robotics person, or we find some library where we can control this robot dog. And when it gets to this, maybe there are two different libraries, and one says to make one more step before making the jump, and the other one says to jump. And then if we were doing this paper and we collected this model-based controller, that means at this state, there is both a distribution of data that says to take one more step and another pile of data that says to jump. And then if we're just doing like using a Gaussian distribution for being able to estimate the outcome for this, it's going to take the mean of these and dive right into the pit that basically exists in the middle. So this is basically starting to be a problem because we don't have a representative enough like function class to describe something that has more than one mode. A Gaussian distribution is a single mode. And very few things, in the real world are truly, well, in practice, super Gaussian. And often, especially when you're collecting data from people, it's really multimodal in the way things happen. So this will get even worse as we do like more and more arm manipulation problems. A little less common for some of these like walking navigation problems. Okay, makes sense? All right. So then there's some nice kind of suspects we can start to use to be able to solve this. One of the common ones to be able to begin with, basically just use a mixture of Gaussians. There's a bit of a hyperparameter here for figuring out, okay, how many Gaussians will we need? Depends on how many modes are in the data set. And that is not a well-known function because the number of modes is actually going to be state dependent on how many modes exist. So these might all collapse to just one mode in some areas of the state space, and in other areas, you might need a whole lot of different modes. And it's difficult to be able to capture this. The other thing that you can use, because there's other type of distributional models. So you could use a VAE, but some might be familiar with those. Those are good, can capture some other modes, but they still tend to be pretty mode seeking. And sometimes it's better to use some autoregressive models. But the tool that seems to work really well these days is a lot of people are using diffusion models. So a diffusion model is another type of like non-Gaussian based model. It can capture a wider possible distribution, so you can capture a number of different modes in here. It doesn't really have to have hyperparameter for how many modes you would capture. And basically this process, I won't go into like as many of the details because this will probably be in your deep learning class if any of you are taking that with Aaron right now. Where basically you take the original image, add a bunch of noise to it until you get, or the original state until you get basically a noisy process, and then you denoise that back. And then from this, you can learn a lot of different types of distributions from essentially just Gaussian noise sampling in the beginning. So you can get, pictures of, I guess, cities in this case. And it works pretty well. And it's been noted in a couple of the robotics papers, things like, they definitely used it in the Octo paper, and I think in the OpenVLA paper. I don't even think they bothered to do this comparison, where they compared using a diffusion model at the end to just using a Gaussian distribution. They also compared it to just using like a really large, like discretized distribution, which can also capture some modes, but you run into like a curse of dimensionality after a little while there. So this seemingly works. Often adds even more compute that you need to be able to train your model, because now you've got a huge model and a diffusion model at the end of that. This is seemingly more challenging to keep stable and train. But this is definitely something to really keep in mind as we're doing, like, especially in the area of behavior cloning. Although, yeah, we'll get into that a bit more near the end of the class. So this works good for behavior cloning. This should seemingly be helpful for RL as well and Kaplan and being able to capture more distributions. It's just much harder to train for RL. So there hasn't been much work that uses like a diffusion policy, literally for the policy that's trained like online from scratch. That still seems to be, I don't know, challenging to be able to get working. Okay. So then from that, just to review some of the behavior cloning and get into a few of the details we discussed. So kind of often, a little bit like behavior cloning is usually not the only thing that is needed, at least to get like really good performance within some amount of error bounds. This is much due to the distribution mismatch problems. It can work well when samples are from a really stable trajectory distribution. So this is often, if you go back maybe 3 years in time, which is so far ago, a lot of the robotics papers, they would still collect data from experts, but you usually have one expert. So like one really knowledgeable robotics graduate student would collect like 20 minutes worth of data, and then you could use that and be able to train a model from that. So that worked really well because of this really stable data distribution. But it's usually for very specific tasks. And now we're trying to expand on all those tasks quite a bit. If you really want to make some progress here, you have to do something like Dagger, like something that's online learning. It needs to figure out how to collect the data so it can learn how to get back on track. And for the most part, better models do help a bit more accurate. So we can reduce that, E term that was a part of this basically big O of error. Try and reduce that with a bigger model. If you can get more capacity there. It is good that we can be able to train models across more data. This ends up being more important. So just sort of as I messaged or kind of passed a little bit there. Let's chat a little bit about why it's better to be able to train a model across more data. So I mentioned here it's good to have a nice stable distribution. What is kind of unique about being able to collect more data? Let's think about data a bit more and unpack it. Do people suspect it's like mostly size, just like sheer numbers here that are most important? Any thoughts?
Not too much repetitive data. Like, let's say data is an image. If the image are too like similar, there's no gain. We're not doing any gain.
Mm-hmm. So I'll say you want some diversity.
Yeah.
Something at least like that, because then you at least have some variation. So if I give you a billion copies of the same thing, not as helpful as at least a billion copies of variety. So then why is that important? Why is this diversity, this variety important in the data?
Generalize better.
Yes. So then where are we getting this from though? So remember, this is behavior cloning. So someone is like literally collecting this data.
Want that someone to be a different person. Because if you're just owning someone's one person's doing something, so you're basically copying Glenn's how like he takes his coffee mug. But in the real world, we should want to see how the whole class takes their coffee mug to try to learn the best way or different ways to do it.
Mhm.
And even with the same person, like, let's say for driving, for example, if the person only drives like from 9 to 12, but it's the same light in the day, not at night or in the same place. So if you drive in different times of day and different places, also requires much more diversity.
Mhm. Yes. Okay, and then I'll add one thing to this. So then hopefully all of those people are licensed to drive. So it's like diversity is good, but it has to be like quality diversity. If I collected a bunch of robot data from, I'll say like kids, or maybe I tried to get my pet or something like that to control my robot, that might actually not be a good thing to put in the data set. And there's a couple of papers that actually show if you have some of this data and you include it, sure, it makes it bigger, but if it's not of sufficient quality, it actually drops the performance of the model that's been trained. So then the extra like little asterisks I want to add into this is the data is really nice because you're essentially collecting a data set that is averaging experts. And when we average a bunch of experts, we can usually learn like a much stronger causal model, like averaging over all of these. So the real stuff, if we're looking at a data set and we're collecting something and we want to know it's useful, it's got to be good quality. It should basically be averaging experts and have some diversity. Because I'm sure, yeah, if we all trained how to use robots in here, and then we trained a model from all the data we collected, that diversity and how we'd all even try and solve the problem a little bit differently, but successfully, is what gives us, okay, no, this is basically an averaging of all the experts that know how to do this and their strategies on how to solve this. Not totally random diverse data. And this is, in a large part, what gives a lot of these models some of their strength. And this is what we want to do. This is why we train, this is why the community trains large language models over the best, 1% of the internet. And then that stuff is like rich in knowledge and ideas.
Yeah, I would say like, example for quality, I think that you need to introduce like some crash in your data set, example, some vehicle crash. And then I would say like in my driving course, we saw some video of people like crashing, and that was like the point was like to try not to repeat that. So, but I would think that like at some point it will be useful to have some data in the data set. But
It's true, especially for RL. Like you need this to be able to compute like a gradient or like if I got a Q value, like what is bad stuff? You at least need some examples, or it just assumes it's a master at everything and then everything is like a Q value of positive infinity. It's not going to learn anything. They probably have some challenges trying to convince a couple of companies that they need to make and include crash data into their own work, partly because they might want to say, well, we never crash, and we don't even need that data. But at the very least, I would say you could also kind of want like near miss data, like going to a crash and then how to avoid that crash would also be fantastic data. So you kind of want the whole diversity from the good to the bad stuff. And then that's what really gives us like this band of getting more on policy data, it'll get into crashes. And then we know all this basically information is available in terms of interventions in our data set and then how to recover from them. So yeah, but if you want to get to the optimal policy, you definitely need good data and eventually get back.
What if we have a situation where we have like 5 experts, that we collect data from each expert, like driving, for example, and now instead of training one model for all 5 data sets, what do we train? Like 5 models, one for each data set, like one expert, and then we ensemble them directly. I'm guessing that would underperform compared to like one model that learns everything. Is that your intuition?
So it doesn't always underperform. And I'll talk about this a little bit more in the next set of slides, but this is essentially like model ensembling. Like if you've got some data, you could train different models over these data sets. And then the performance part though is where this conversation gets a little tricky, because like you're talking about performance probably in terms of getting like the best like result that maybe doesn't crash. And it'll do that. It'll eventually, if you have some model that's in trying to figure out like which experts to pick at each state, it'll eventually learn how to pick which expert that does better there. But I think part of your question is, okay, will this scale well or generalize well? Because now these ensemble members, they don't talk to each other. They're just kind of like, they're stuck in a room and they used to push a button or something that says how to do better here. So you're not going to learn as much reusable structure across ensembles. And that's where, I don't know, the math sounds nice, but the reusability and like ability to like generalize more might break down. That's where it's hard. I have seen a couple of neat network models that mix these two, like maybe a lot of the model is shared, and then a small part of it ends up being the ensemble at the end. I think there's definitely a couple of options papers that do this, where like the vision part of the network is all shared. Because essentially, I hope we all kind of want to learn the same like perceiving function of how to get the world, but our decisions might change. So then I'm on different heads at the end of the network that are all slightly different ensemble members for figuring out whether or not you should try a different policy or Q function there. And that at least has worked a little bit better. Because the challenge of doing ensembles of models is usually one specializes, literally because it gets picked more often, therefore it gets to see more data. And just because of the process of seeing more data, it's more likely to do better. And it just, one of them just kind of skyrockets up to being the best model and takes over the whole thing. So it's really hard to balance your ensemble and get your success there as much as you want. Yeah. But good, that's sort of a lot of the part of this class is understanding how to deal with these kind of boundaries and mixtures of models. Okay, So then, yes, this is just sort of the part that I was pointing out. It's really nice because you can learn over a mixture of experts, so you'll probably get an even stronger causal model. And one model that basically should be like more robust to the assumptions of each individual expert and still be able to perform well. Okay, so, and this is at least the first, I don't know, AI generated image I've used in my slides so far. But, so this is gonna be what I'm calling the curse of T that I put together, because we haven't really focused on it too much. And I don't know how much everyone has yet like looked and read into the details for these different papers. But one question I'll definitely ask is, we talked about the fact that error accumulates according to T. All right, so then how many people paid really careful attention when reading your papers? How big was T for when they were collecting data? That's a weird question potentially, but for the BC0 paper, they mostly collected trajectories that were like 40 to 50 steps, things that were like 1 to 2 seconds. And then they're training this behavior cloning model to be able to perform well within those 40 to 50 steps. And that might start to be like a comfortable kind of hard cutoff. But like, okay, once you start to go beyond that, maybe behavior cloning doesn't work so well. And that's part of the challenge where you got to be careful of this curse. The longer you try to extend T, the harder it's going to be to have your behavior cloning model stay on track. And you'll see in a lot of the like experiments and examples in the papers, they're going to pick trajectories that are usually like less than 2 seconds long. And the stuff for like the SECAN paper, like every kind of trajectory is more like half a second. So like they're picking these things very carefully. And whenever you read a paper, you should kind of understand, okay, like what is the amount of time this thing is actually meant to control? And they're gonna pick a model on the amount of data that is needed, partly because of this effect of how much T is gonna be something to like struggle with as this ends up being good and controlled. Does that make sense? Question so far? Okay, because, there's one way, sure, you could try and improve your overall model to be able to reduce your average error across the whole state space, or let's just reduce T, or like basically pick tasks such that T is actually pretty small. It's not the self-driving car problem, which is where you have to stay on the road and not make a mistake for potentially hours. You've got to not make a mistake for a second and a half, which I would think almost every person in the world is kind of good at doing. Like you're all at least not knocking all of your stuff off your desk right now. Not too hard to manage so far. Okay. So then think about that. Like, what is the average T in some of these papers? Because the goal is we really need to be able to extend T. Like, if we want to make some AGI system that helps with a whole bunch of stuff, we're going to want to give this thing pretty complicated long-term tasks. Like maybe it is like go drive and get groceries or something like that. This is going to potentially take an hour, depending on where you live, not 1 to 2 seconds. So when you're looking at especially these larger models for robotics, they are still trying to keep that T really small, especially in the behavior cloning examples. But yeah, and then so then we'll maybe get into a few papers for this for sure. And then there's different ways to try and control this, to try and extend T even in a practical sense. One of them is to use some the error for your model in reducing T. Because now you have to predict something that has more dimensions, but at least you don't have to do as many predictions. This is another way to try and like play with the terms basically of this error cost that the agent is going to ensue overall. And there are many other ways, some of them a little less obvious than just doing this. Okay. Questions? Good. All right. Okay, so this is where we talked about behavior cloning a fair bit. There are many other ways to basically do versions of behavior cloning that fall under the umbrella of imitation learning. So it's kind of broadly defined as let's make these two distributions match in some way. And there are many different ways to be able to do this. Behavior cloning is one that's going in popularity a fair bit. It's pretty easy to be able to code up and use and collect data. There's also learning from demonstrations, which is very similar. Inverse reinforcement learning, where you're kind of like doing behavior cloning, but you also want to learn the reward function of the expert that was optimized to collect that data. Sometimes helpful if you want like the reward and not just the behavior. Different types of distribution matching, some adversarial methods. And then the somewhat trickier version of this is also doing this when things are extremely partially observed. So a lot of these mathematically work on states, and when you get into the partially observed areas of trying to do this matching, you kind of like lose a lot of the guarantees there. And this is really what we're trying to do these days, is figuring out how to do partially observed behavior cloning or imitation learning, because we just get images or whatever other sensors we may have available to glue onto the robot. So if you're very interested, you go check out this survey. Otherwise, I'm just going to give you a little bit, I guess, after this introduction to inverse dynamics, which is also like another algorithm that can be used here. So, okay, so inverse dynamics is kind of it's not a totally weird version, but it's a little bit different than the way behavior cloning works. So here, in many cases, we've been talking about doing behavior cloning, which is we want some model, we'll feed in some state, and we get out some action. And then we can train the model to be able to do this. There's a different way we can end up doing this, because maybe we don't have a lot of action data. And that's why we're talking about partially observed models. We could potentially have none. So then what can we do in those particular states when we don't have a lot of action data? Well, one kind of interesting thing we can do is basically train a model that outputs an action, but you give it basically the state at t and the state at t+1. And instead of the reason, and this is called an inverse dynamics model because an actual dynamics model is always state action next state, like t+1, t and a of t. And then here we're kind of inverting this model so we can figure out what is the action that actually led from one state to the other one. And this can be nifty because then maybe we don't have a lot of data and we can just train this model to be able to output actions. Because then when we just have states, tons and tons of images, observations, afterwards, we can basically use this model to label all of that data with actions. And then maybe use one of these other algorithms here after that to be able to train the policy. So here, I'll give another more detailed example here. So this is basically the idea where if we've got, this or some image, what was the action that went from the image on the left to the image on the right? Maybe some of you, could take a second, think about, might be actually pretty tricky, to try to understand what was the particular joint torques that resulted from one image to the next image. It's actually kind of, tricky to figure out unless you're like, have spent a long time trying to study motion and to figure out how the dynamics change. But the whole question is, all right, if we can understand what action caused these, then maybe we can train them all to be able to produce those actions and use it in all those other behavior cloning methods. That'll work well. So this is helpful. This is a very common use case where basically we have tons and tons of observation data. So like we've got YouTube, maybe, or something like that, where there's whole piles and piles of video. And we only have a small amount of this where we actually have actions. So maybe there's tons and tons of data of people playing video games on YouTube. If some people like to watch other people play video games instead of playing those video games themselves. And then from this, maybe there's one particular video game that you're interested in, and there's only a little bit of data of someone actually controlling the mouse for that game. But you want to collect like an agent that'll do really well in that game across all the possible states in the game. So hopefully you can get some transfer from these other games and be able to label all of the actions for this held out game or low data game. And this is what is done in one of the recent papers that was part of the reading list, where basically you can train this inverse dynamics model on this big or the small pile of expert data, and then use it to essentially label all of this like in the wild data in order to get the actions that are needed to be able to train using those other algorithms. And this is what was used in the video pre-training paper, if that was one of the ones that you read for this week. were basically is this process and worked really well for being able to do this for Minecraft. Because for Minecraft, there's tons of people like playing Minecraft on the internet. It's actually always a good example because there's tons of data on the internet for this particular one. So there's plenty of data you can train from. And then I think at the time they could just collect a little bit of data amongst themselves, or they paid a few people that are actually playing the game to collect some of that expert data, and then use that IDM model they trained to go back and label like all of the YouTube data for people playing Minecraft. And then you have a huge data set that you could train like some behavior clones model from this or other types of models as well.
Just a short question. When we, the actions in the case of Minecraft, for example, are there like mouse clicks, keyboard presses, or would you like to go further and think in terms of joints and what would be the underlying embodiment of the role?
So for this data set, it looks like they're using mouse clicks and actions, just according to this little diagram. And that's just like the interface that the computer provides. But what I would want to add on to this is, well, at least in this room, we kind of have the lucky ability and power where we can make this interface however we want, whatever we think is going to be best. Yeah, potentially. But I think maybe part of the point you're getting to is this is maybe a nice outcome. I'd be more impressed if there was like a humanoid robot sitting in a chair playing this game, controlling the mouse and the clicks than it is using the direct Minecraft interface. Because it's really hard to transfer data across these interfaces. Like one of the most challenging things right now in behavior cloning in RL is if you have a different action space, it's really hard to transfer that to some other task, even if the data looks similar. So I think part of the hope as well in some of the humanoid robotics companies is like, we've built, our world to interface for people. So then if we make a humanoid robot, it can use all the same physical interfaces we use to control things. And we don't have to make custom ones for every interaction. So like, if you want the best agentic model in the world, make a humanoid robot. It already knows how to interact with everything. You don't have to make interfaces for everything in the universe. Potentially, just a suggestion. Think about it. Okay, any other questions about VPT? Okay, you sure? This is basically the last question on your homework assignment for your first programming homework assignment. All right, I'll expect more questions in the near future, but no worries. This one's not too bad and the details aren't too challenging, and it's kind of easier to train than some of the uglier stuff that'll come up later in the class. We're not into RL yet, thank goodness. Okay, so this is basically like the outline for the algorithm. Like I said, collect some sufficient amount of expert data such that this can be used to be able to train now this inverse dynamics model. Use this to label all the states that you have over this larger data set, and then train maybe some behavior clone policy on this expert data, and then just run that in the world. And now you've got some behavior cloned expert policy that has much more support over the whole state space than just the expert data that was collected. Still need to collect some expert data for this, but you don't need a lot, and it's actually rather easy to debug. It's always a nice feature of some of these algorithms. Sort of like, did your expert data set actually include like any states that this might have to view at some point later? Did the expert data actually ever push like the down action in the entire process? And you can investigate that. Or you can just look at two states, if you're looking at something like Minecraft, and see what action it tries to predict. And you've got the simulator there too to say like, well, no, it should never try to select that action. So in practice, for this particular algorithm, a lot of the components for training it are not as like obfuscated. Like it's easy to see what might be going wrong. You don't have to really dig into and try to understand the network dynamics as much. So it's pretty nifty and probably why it's gaining more and more popularity to be able to train these models. Yes.
For this paper, did they, because you would also need to know the kind of characters, like dynamic, like if you were playing Minecraft and you fall off a cliff and you're not controlling it, but your images are still changing because you're falling. Like, do they have to take that into account, like the velocity of the character, I guess?
They don't take it into account explicitly in the paper, but yeah, that's part of, okay. So that is one of the subtleties and weaknesses of inverse dynamics models is because one thing they can't actually do is figure out causal mechanisms for how the world unfolds. It's just trying to make this connection. So it might have a hard time understanding that changes are occurring right now that are totally out of its control. And that's one of the challenges of IDM models. So they can work better for things that are like slightly less partially observed, or when there's not a lot of stuff out in the universe that changes without, not aligned with the agent's actual action. But that's actually true of like the vast majority of models we'll talk about, like the ones that are working. I think a whole open question in robotics is really how to deal with all the other stuff in the world. So like the behavior clone models we talk about, sure, there's some visual diversity, but it's not like it has to interact with other people in that actual clip and deal with that. And we will all behave differently. And it has to figure out how to like model the entire like human cognitive process to figure out what's going on. Right now, it can move pixels from here to there. And there's definitely some work to be done. All right. Okay, so then there's, like I said, a couple of other models that can be used for different types of behavior cloning. Right. So this is the basic behavior cloning we've talked about. Collect a data set, basically train your model to match this well, get high log probability over the states that exist. This is really easy to use. I mean, I hope people can like learn to appreciate this a bit more, but often algorithms take off because they're not complicated to use. If you make a wonderful theoretically correct algorithm, but it is the most complicated thing to tune, apply, or explain to other people, it'll be a hard time before it ever catches on if it does. We have simple algorithms that work well. It's much easier to like scale those up, give them to other people to collect data, etc. So that's something to keep track of. And like we said, suffers from some distribution mismatch issues. So how do we get around those distribution mismatch issues? One way is to use inverse reinforcement learning. So this is very much like behavior cloning, except for it's going to learn an extra function to help it actually reduce error much better. So you're basically in this process, it uses RL, but the idea here is actually part of the learning process is not just, you don't directly do log probability on the actions that your policy or the data from the data you've collected. Instead, you use this to learn a cost function, essentially a reward function from that. And then you train the policy to match that reward function. And then this cost/reward function is basically optimized in such a way that you want it to have a high value for the expert data and a low value for the policy. So then it should be able to separate these two. And then as your policy or training gets better and better, it becomes harder and harder to tell the difference between the expert data and the actual policy. And then you start to get a good cost function and a good performing policy in that case. And then there's many versions of being able to slight variations on this algorithm. And this, because we're using RL in this case and a cost function, it has like really small error bounds in terms of how well it'll match the expert. And related to the conversation a minute ago, though, it is also a somewhat complicated algorithm. It's hard to get working. You now are also training a policy and a reward function at the same time. The dynamics between these two are not so simple. And for the most part, some people are working on this, but it is very difficult to scale because of this. It's kind of a bit unwieldy. You have to have even more knowledge about how the system works in order to train policies from this. However, it would be awesome if we could do this because for the most part, having the reward function is really helpful. It's a bit more generalizable than just having your data set. Here's some data. That's great, but what if I want to control myself over in this spot? Well, if I had the reward function, I can just use it and train my policy there. But if you don't, there's nothing you can do. Kind of hope that it will generalize there. And well, I don't know, my research doesn't really run on hope, and hopefully your practice won't as much either. The smallest amount of hope possible, what you want to aim for. Okay, does that make sense? All right, and then there's just a few other variations on this. Some people might be familiar with GANs and adversarial methods. So here you can do something similar where you've got some discriminator instead of a cost function. And basically you have two distributions, your data set from your expert, where your discriminator should basically answer with a 1. And then everything that comes from your policy, it should actually answer with a 0. And this thing is meant to discriminate between the expert stuff and your policy stuff, which is bad. And then as this trains, you basically reward the agent to get higher and higher, more close to the 1 values that are outputted from the discriminator, such that over time it'll eventually get higher and higher reward and look more and more like the expert data distribution. It's got a lot of similarities to the inverse RL example. This is like also a little bit more challenging of an algorithm to get working. It's not used a lot these days compared to other algorithms, but still can work pretty well. You just have to be really careful about how you kind of like train this now discriminator and your policy, because now you still have to train these two at the same time. Okay. And then, yeah, the last part is just partially observed imitation, which is not a totally different algorithm, but just the concept that for these algorithms, there was normally like a state and an action, and there are some guarantees that you can match your expert distribution there properly. And when we get into this where we have observations instead of states, a lot of those algorithms don't work. Well, they may work, but theoretically, there's definitely some challenges and hurdles. And there's like an example of Gale that does from observations, that can still be able to match this distribution. But really, this is the challenge these days, is figuring out if someone gives us big piles of data, even which algorithm should we use? And it's going to be from observations. Basically, every robotics problem is truly a partially observed problem. Whether or not you actually just care about the stuff outside of the room, doesn't matter, it still exists. And if you want it to eventually go out into the hallway and be a fun AGI system, and I don't know, go grab pizza for everybody in here, it needs to understand how to perceive the whole world and be pretty good at it. Okay, and one way to be able to do this is actually to try and use some like inverse dynamics models for estimating the changes between observations and the actions that would cause those. Okay, so just to cover a few of the main points. So I guess we did a few of these already. Agents can be trained across more data. Yeah, we already talked about that back in a few slides. Okay, so there's a couple of links here to some code just to get familiar with things related to the class. We'll be using like PyTorch for the homework assignments. And here is just like something that's using an experience memory. It's basically a large buffer. And like normally when you're doing behavior cloning, your data set is fixed. Our experience memory is basically a queue that, you know, whatever was first into this queue is one of the first things to leave this queue and is always of some fixed amount of size. Because as we're collecting data, we might want to be able to throw some of this stuff out. For the most part, for the first assignment or two, this will be fixed because it's like given to you as you train a model, more or less. And you can also look at, yeah, so this is more related to some of the details and being able to get the algorithms to work, is state normalization. So if you're taking inputs from any random robot you're trying to be able to train your model from, the scale of the like literal features for the observation space can often affect learning. Like neural networks are really like they're more happy when their distribution of input stays between like -1 and 1. If we start giving inputs to these models that are somewhere in like the hundreds or thousands, well, they're going to give outputs that are an order of magnitude according to that as well. And that's going to cause huge losses and probably destabilize your whole training pipeline. So some of the simple tricks people use is basically to take the original state and divide it by like the standard deviation of everything that was in the experience memory, something like that. So you're essentially like, this is called whitening the data or standardizing the data such that at least the statistics are not too ugly and they don't change much. And especially if you don't do things like this, it's really hard to have useful learning rates because a learning rate is kind of dependent on like the average loss that is computed from these models. So if you have inputs that are like 1,000 times larger than being between -1 and 1, you're going to get outputs 1,000 times larger. So kind of an equivalent thing is then to take your learning rate and then multiply it by like 10 to -3 to make it 1,000 times smaller. So in some ways, a lot of these state normalizations are just trying to keep all of our loss terms somewhat meaningful across algorithms, across environments, across robots. And then we have less things we have to worry about tuning. Okay, does that make sense? Yeah, so it's usually not something we worry about as much, like as researchers, and people working on robotics, because when you're working with images, the normal state normalization is fine. You just divide your pixel space by 255, and then everything is between 0 and 1, and you're good. But in all other things, when you have like proprioceptive sensors or IMUs or other things sensing velocity, you can have large numbers that come from wherever. You need to, it's helpful to have a better system to track and normalize these. Okay, any questions? All right, great. Let's take a break now. Seems about perfect timing. And then we'll come back at, yeah, 2:28.